I hope you can able to see my screen, right?
Yes, sir.
Yes.
Okay. So a brief summary of what we are trying to address in the last class. Primarily, we are trying to learn decision tree as an hypothesis. So our hypothesis set now contains Boolean formula which can be disjunctive also. That means it could be ANDed and ORed. However, the representation that we will use for an hypothesis to answer is in tree-like format. So we call it as a decision tree. And if you remember correctly, the decision tree we build in this way that we have an attribute, we select an attribute, and depending on the values of that attribute, suppose this attribute A1 can take 3 values. So depending on the values of attribute, we decide upon whether which is the next attribute we can select so that we could categorize the classification problem that we have in our hand with the training examples either in a positive or negative classes. For example, we are only looking at the classification problem having a finite number of class, and for simplifying our analysis we used only positive and negative classes. So this is how the decision tree look like, and therefore your primary decision making at any point of time was that which attribute you will select. And in order to select which of the attributes, we introduced two kind of measure. One is information gain, and the other measures that we introduce is something called Gini impurity, just to show you that we could use our own measures also to dictate this. However, we need to differentiate that whether this attribute which we are taking as a best attribute is splitting the space of our decisions into a greater extent. That is our only concern. And we have also seen that this information gain actually builds up upon a concept called entropy, and this Gini impurity builds up with something we call as a Gini index. The concept we call as a Gini index. So we have also seen the definition of an entropy is if we have C classes, then we say E equal to minus summation of, let's say, C equal to 1 to M number of classes we have, then this into log as our entropy. And we also perform that when we choose an attribute, then the space of training example gets splitted, and we say that our information gain is whatever be the entropy earlier minus we sum over to the fraction of that space splitting. With that, we compute the entropy of that split position. So this is the gain that we get, and higher the gain, better the attribute to be selected. Similarly, instead of entropy, when we used Gini impurity, our Gini impurity decision was just the formula changes, and we also have seen that this kind of a formula helps us because this is computationally easier. So with that note, we closed our previous class by saying that there are certain things we will try to understand from this type of learning. So effectively, our hypothesis space that we converged upon is set of decision trees. So that is how we represent our hypothesis to answer, and our learning algorithm was decision tree learning algorithm. We call the first learning algorithm that we saw as ID3 algorithm, which selects the attribute based on information gain and then splits up and selects the next attribute based on information gain. So that is what we studied in the last class. So going forward, the first question is that how do we make the search in the hypothesis space? Because here, if you see that our hypothesis space is a set of decision trees, therefore there could be many possibility arising through which we will search and finally represent our the golden hypothesis that will abstract out the unknown function, that will approximate the unknown function. Therefore, the next question is how this searching happens in the hypothesis space we have. So you can see that in case of candidate elimination algorithm, which is a batch algorithm, we see one of a candidate training example, and then we try to refine our version space boundary a little bit. So if you remember the pictorial description of the candidate elimination algorithm, here is more specific boundary, here is more general boundary, and we go on refining the general boundary as well as the specific boundaries. Based on if we get yes example, we go this way, we get no example, we come down this way, and in between whatever we could represent is our version space or all the possible hypotheses that we could result. So here the search is basically looking at every attribute which of the combinations of Boolean ANDed formula that we could represent, as we have seen in the previous lectures. However, here you see at any intermediate point when you reach, you have a tree built based upon certain attributes. Suppose this is the tree up to that point being built. Now you were discussing what to select in this side. Then there could be multiple possibilities to select from this side. One possibility could be that you select, for example, so this side remains the same. Suppose, for example, I select A1 as an attribute and then go on splitting and finding out what happens. Something that could be that I could select some other attributes. Let's say A3 and go on, see what happens. However, let's say the best choice become A2 and we go on searching the path by selecting A2 from there. So therefore, you can see again after this point, so since these are already classified as negative, plus and minus, after this point, there are two positions. Suppose I got negative here, then what will be my choice here? And we move on depending on all possible paths that is there in the hypothesis space. So as you can see, usually this is a search procedure where we are using best first mechanism. If you remember AI search, that whatever be the best option to classify the data in a better way. What does this best first is trying to do? It is trying to prefer shorter hypothesis, because if I select this very well, if I can select my A2 very well, then the chances that it will classify it quite easily, meaning that the height of the tree will be lesser. That's why the hypothesis will be shorter, because the depth of the tree means that what do we mean by this depth? It means some attribute here gets the value v1 and some attribute here gets the values, let's say v2, makes it plus. So higher the depth, the longer the formula inside, and the higher the branches, the longer the formula with respect to OR. I hope you can understand this very clearly. So therefore, by preferring best attribute at the next position, we are curtailing the height of the tree. That means we are curtailing the length or the hypothesis length and preferring to shorter hypothesis. However, this kind of search do not use backtracking, as you can see, because every time we have a best attribute, we go on. No time we come back and then search for alternative routes for a better attribute. Unlike the best first AI type of search, whatever you have seen till now. So this, therefore, you can easily see that though your hypothesis space is complete, that the set H through which you can reason. So set H contains every hypothesis. So this could be your hypothesis 1, this could be your hypothesis 2, this could be your hypothesis 3. So the whole space is actually complete. It contains every possible hypothesis. However, you are navigating that space only in an incomplete manner by your best preferred hypothesis attributes, and therefore you are not searching this whole space in a complete manner. You are incompletely navigating through the space and finding out your final hypothesis H, which could approximate the unknown function. So clearly now the fundamental difference with the candidate elimination algorithm is, in our case, is, see, in candidate elimination algorithm, we try to navigate through a version space and come up with a set of hypotheses inside the version space, which all of them are actually fits with the training data perfectly. Now, if you look carefully at this version space is basically incomplete. Why? Because I am not allowing this kind of operations in the version space. I only allow Boolean and formulas. So candidate elimination algorithm searches in an incomplete space and come out with a hypothesis, whereas decision tree algorithm searches in a complete space, but searching comes incompletely. Here you see in the version space, if you look at this diagram, in the version space, I search completely because everything, whatever is not a candidate, I eliminate. Rest of them, I keep it as it is inside my set of candidates that I could see as a potential hypothesis. So if I try to draw an analogy between these two algorithms, so here I write candidate elimination. Here I write decision tree. So in candidate elimination algorithm, as you can see, it is incomplete hypothesis space, whereas here my hypothesis space is complete. However, candidate elimination algorithm searches completely with respect to the version space or hypothesis space it has, but decision tree algorithm searches incompletely the version space it has. Therefore, you can see the if you remember, we have introduced a term in our concept learning which is called as inductive bias. So this term says that if what is a bias here in our concept learning algorithms, that I am assuming my hypothesis to be only formed by Boolean ANDings. Therefore, the inductive bias of candidate elimination algorithm is also a restriction bias, in a sense that I have restricted my hypothesis space in an incomplete manner, though I am searching completely there. Whereas if you try to find out the inductive bias of my decision tree, it is basically a preference bias. We call in colloquial terms it's a preference bias because I have a complete space, but I search incompletely based on my preference. So although these two are having a bias which we call as an inductive bias, but one we call as restriction bias because it has a restricted space through which only it can produce hypothesis from, whereas in decision tree algorithm it has a complete space that anything could be possible. However, it preferred one particular types of path and therefore a particular type of best attribute preferences. and it gives the answer. See, the question is that we, through this answer, finally we get a representation of the decision tree. But our question is, how well does it mimic the behavior of the unknown function? So it is not obvious that if we select the best attribute, that only can generalize well over the test data that we have. Maybe that this hypothesis was better. However, that is why we have a preference bias. We are saying that this bias, finally the hypothesis that we get using such kind of incomplete searching, using preferences of attributes, would lead up good fitting to the training data. And as per our inductive learning assumption, this training data fitting well will also approximate my test data fitting well. So this is a very important point to note about the bias and our goal that we are trying to achieve. I hope this point is clear. If you have any questions, you can ask.
So can you repeat this inductive bias? So
Okay.
what was that?
So first of all, what is bias? Bias means that you cannot learn from an infinite possibility. So it comes from a domain knowledge of the problem that you are trying to solve. So that is what bias, the term bias means in machine learning. So you have to provide the machine a little bit domain information or little bit bias it towards selecting some final answer. Now, in case of concept learning, when you see candidate elimination algorithm, you will find that how candidate elimination algorithm works. It has a whole set of hypothesis space to start initially, specific up to general boundary. You see, our general boundary is everything can be possible. Our specific boundary is nothing can be possible. However, in that space, every hypothesis is present, provided that hypothesis space is incomplete because I only allow ANDed Boolean formula. However, candidate elimination algorithm searches over that space in a complete or exhaustive manner. Whichever does not fit the training data, I eliminate. The rest, whichever fits the training data, everything, every hypothesis is present inside it, and I report it as my final hypothesis.
Yes,
You
sir.
choose
Rest is
anyone.
clear.
Yeah, that is the restriction bias because I restrict the hypothesis space. Whereas this one, you can see that I can start with any searching point, and this is my full search complete hypothesis space where if I select A1 attribute at the first, A2 attribute at the first, or A3 attribute at the first, every path will lead to some search paths in this complete hypothesis set. See, in a decision tree, what can happen? If you have three attributes, either you can select A1 and decide upon, or you can select A2 and decide upon, or you can select A3 and decide upon. However, let's say
we decide a greedy approach.
Yes, we decide a greedy approach, which is a best fit attribute. Therefore, what we do, that's a preference.
That is only in the case of first attribute.
No, every attribute we do. That's a recursive procedure.
Yeah, it's a recursive procedure.
So that's what happens. First, you select A2. Then what will happen? Let's say A2 makes it this one positive, but this one it cannot decide. Then again, you need to select some of the attribute value, which it could decide depending on your preference. You are not trying out all possible options and searching the complete space, but you are restricting with an information gain and making it as a best one. So that's your preference.
Yes.
Therefore, what you are doing is that you are only searching a particular path in that whole space, not fully. So you are searching it incompletely. And that is what preference bias means.
Sir, could you explain candidate elimination again briefly? I could not understand.
So candidate elimination means you have a hypothesis space, which means that you have certain values of attributes, and something could be like this. So this is a particular hypothesis. Let's say I call it H1. So there are many such in this. Now, when you get a training example, it could be characterized as yes or it could be characterized as no with this set of attributes. And this is your training example, how the training example looks like. Now, taking a yes example, what you do, yes means in this hypothesis space, if you don't allow anything, then this will not pass. So you have to at least allow these values of the attributes. So therefore, you just relax a little bit the space, not saying that this is anymore my attribute, but from here everyone is possible. And this space is basically this thing I need to allow. That's why I need to relax a little. So for a yes example, you shift the specific boundary a little bit. For a no example, in a similar way, you shift the general boundary a little bit. Finally, you reach upon a point where these are satisfying every training data you have. That is satisfying, meaning that the hypothesis that you give like this, if you fit in the training data, it will say yes or no depending on every hypothesis you have in this space. So therefore, we call this as your version space where all attributes successfully characterizes your training example. That's how candidate elimination algorithm works. So it eliminates candidates which are conflicting with your training examples.
Yes.
Okay.
Thank you. Understood. Yes.
So that's why it's a restriction, because you start with a restriction handed Boolean formula. It's
Hello, sir.
and yeah.
Sir, which is the better means the candidate elimination or decision tree algorithm? Because it is the incomplete in candidate elimination, but it is complete.
Yeah,
but
because
decision tree complete, but there the search is incomplete.
See, it depends upon if you know what will be your hypothesis, and it could be made as ending of Boolean formulas. You can use this one because it searches completely. Your
Yes,
incompleteness factor is only the ending of Boolean formula. But if your formula does contain disjunction, then you have to go in decision tree, because disjunctive formula you cannot handle by this.
Yes, sir.
That's what.
Yes, sir.
It depends on scenario to scenario and depends on the applications. Later, we will see there are more advanced algorithms of this classification problems that we are targeting. We are targeting classification problems. So
Yes, sir.
later we will see other algorithms too. I mean, then you will find out that depending on the scenario and depending on what you want to do with the data, you can select your algorithms in that sense. Okay. So now, as I was saying that it's using a best attribute searching method every time. So every point you are using a best attribute next. So first I use best here, then I use best here. So the point is that best means that I could categorize and finish my tree at a lesser depth, as less depth as possible. My decision tree, if it is lesser depth, that means it could be generalized more. Can you see the point? Let me draw and explain. Suppose you have a tree like this on attribute A1. I do something, then I select attribute A2 here. Let's say I can classify. If I select attribute A2, I can classify. If I select attribute A3, I can classify like this. Now, what does a path in the decision tree mean? So you are only bothered with this positive paths in the decision tree. Now see what this paths means. Suppose A1 has V11, this is V12, this is V21, this is value 22, this is V21, again this is value 22, this is V31 and V32. So therefore the decision tree results, if you write the formula, it will be V11 and V21 or V12 and V21 or V12 and V22 and V32. If this is satisfiable, then every training example satisfies this is a yes answer for you, because this is a yes, this is a yes, and this is a yes. I only characterizes these three paths here. So you can see the depth of the tree determines the hypothesis would be longer or hypothesis would be shorter. See here. So therefore, if you could select your attribute in a best possible way, meaning that you could end up by making the decision tree of lesser height. Therefore, best attribute selection makes two things. One, your decision tree shorter, which implies your hypothesis also to be of shorter. But why do we prefer such kind of a thing? The primary reason, let us say, what is the difference between these two? Let us try to understand.
So I had a question.
Yes.
So in the decision tree you made, all the endings are either positive or negative. But the
Yes.
approach we use to find the attributes for a decision tree, it depends on either some kind of a gain or it depends on Guinea. So how do we get assured that all the endings we'll have will be either plus or minus, like positive or negative?
So there could be three options as the ID3 algorithm. So let me just repeat the ID3 algorithm, then you can understand. See, there could be three options possible in ID3 algorithm. One is choosing an attribute for a value, you get all positive, then your leaf node will be positive. Or you get all negative, your leaf node will be negative. You get this point, I think. Right?
Yes, I get it.
Yeah. Now, the question is that it may so happen that your attribute space vanishes, but here you get 3 positive and 1 negative. What to do with that?
Yes, sir.
So you go by majority in that case. If there are similar, you go by a kind of some kind of your pre-assumption that I will give plus the best more preference, and you end up. Suppose
Okay.
there are only 3 attributes, and I lead up to a situation where after selecting A3 in one branch, I get 3 plus 1 minus. Then I could not directly say it is a plus for all, but since I have to finish off, so I will say that leaf is positive because it has very less training error if I consider this to be positive, because only one or example might be a failure in the training set.
I understood. Thank
Yeah.
you.
So the question that now I am trying to make is why we are trying to prefer shorter hypothesis over the longer one. So if you try to see that how the shorter hypothesis will look like, shorter means your ANDed formula depth will be shorter. So that means suppose some hypothesis looks like V11, V21 and V31 for example, and some hypothesis looks like V11 and V21. So according to the selection procedure by which I go, I prefer this one. Why I prefer this one? See, this is attribute 1 value, this is attribute 2 value, and this is attribute 3 value. Similarly, this is attribute 1's value and attribute 2's value. Now, what does ANDing means? ANDing means you are restricting.
কোথায় রেখে দেখে জানে ছোটটা খান ছিল কথা গেল এটা আমার যেখানে এখানে তো হয়েছে বুঝছি
Sorry. So ANDing means that we are restricting the number of cases that could pass with this. Suppose you have 3 attributes and you made all of them like this as a formula. So therefore, in the test data, if I give you a test data, only this thing will pass. Whereas if this be your solution and I give you a test data, you can pass V11, V21 and V31. You can also pass V11, V21 and V32. Both will be passed if I give this hypothesis as my answer instead of this. So what does this mean? See, if some tree gets you this hypothesis and some tree gets you this hypothesis, therefore both of them are a good fit for the training data you have in your hand. That's why you land up into finalizing this hypothesis or this hypothesis. So we are assured that we are fitting good for the training data. But shorter the hypothesis, the number of test data it could generalize, which is not present in my training data, are better. That's why people prefer shorter hypothesis, but there is no theoretical proof on such thing that always shorter hypothesis will result, because you do not know, maybe this one is a no in the test data. But as I said, that probably we could approximate better with generalization. And this principle, since it's just a conjecture, it is nothing to be formally proven, but it has been seen with the examples. This conjecture is known as Occam's razor, which says that you prefer the simplest answer that you could get, because that obviously generalizes well. But Occam's razor has, I mean, the pro and the cons, both kind of statement for and against it. So one of the thing that we will see from the Occam razor, that it will generalize the unseen data well on a probably approximately correct sense. That's why people prefer this Occam razor, and theoretically there are proofs why this Occam razor, looking at the training data given the number of samples, how it could generalize. So in decision tree, we just follow this principle as a conjecture and follow this Occam razor to make our shorter preferences. The most important question with next comes with the decision tree is, as we are discussing about, the length of the tree is a dictator that how we fit our training data and how we allow more test data or less test data into it. So as you can see, if your decision tree becomes higher length, that means your hypothesis is very much fitting your data, it's too much fitting your training data, it will be less generalizing the test data. We call such a phenomenon as overfitting. And it is a very common phenomenon in machine learning, primarily in decision tree learning. What does formally overfitting mean? Suppose you can create a hypothesis H and you can create another hypothesis H dash. So your H makes less error in training, but more error in testing. Whereas your H dash makes more error in training, but less error in testing. Then we say formally that the hypothesis H is actually overfitting the data, because it can only fit the training data. That's why it is making less error in training, but it cannot generalize the test data well. So generalization factor has been less for H. And we say H overfits badly than if we select H dash. So what does this mean is that, let's say if we try to draw a pictorial description of this overfitting, then suppose this is the number of nodes in decision tree, or maybe the depth of the decision tree, and this is the error that we get. So let's say for testing, what will happen initially when you start off for your test data, for training data, initially you start off, you just grows on error, but after a certain point you will see that the error minimizes when you can fit data very well, and it goes on minimizing, because this is, you are fitting every training instances, so your error is getting minimized. So each time you are getting a new training instances, you are trying to fit it in your decision tree. So your decision tree is perfectly saying well all for training data. Now when you go for testing, then what it will happen is that after a certain point of time, you will see that your error is actually not diminishing. That means you are you are fitting it in a very accurate manner for training, that losing the purpose of generalization. So somewhere we need to make sure that somewhere down the line we need to stop, and we call this gap as our generalization error. So this is your training data and this is your test data performance. So this is a very common phenomenon that we find, which we call as overfitting. Now, immediate question comes is that what are the remedies? So common sense, can you answer what will be our remedy here?
Sir, relaxing the parameter.
Means you are saying, you see here, relaxing the parameters means I need to cut off the depth, right?
Yes,
Because
sir.
more depth means one path is more stringent, less examples will be generalized.
Yes, sir. Yes, sir.
Yeah, very good suggestion. So one suggestion is do not grow the decision tree after certain depth. That is one possibility. Or you may grow, but prune it also. Okay. But how can we do it if we have only training data in our hand? I could
Sir.
not see that how it will generalize over test data, because someone has given you a set of training example, let's say the COVID data, and said it has a prediction that who has a COVID or not. Now you have to go to some random people and have to test it. You do not have the test data before you get the model. So then what you will do with your training data only?
So dividing the complete training set, whatever we have, into a smaller test set and remaining as a
Great.
training data.
Great. So what we will do, we have a training data set. We just divide it, some of the example as our training data and some of the
And as a
example,
validation data.
yes, for the validation data. Usually we do it 80%, 20% category. If we have a sufficiently more data, we usually divide it 80%, 20%. Then what we will do, we will train on those data and try to fit the test data from this validation set and find out whether it is doing good or not. If it is not doing good, either we will try to prune or do not grow the tree up to certain depth and see how it is doing again. This is called, this particular phenomenon that your friend has declared is called training and validation approach to reduce overfitting. Other thing, just a little bit of ramifications from this approach is that though you split in 80%, 20%, but you split randomly 10 times. So you can see the ramifications. If I do this thing 10 times in a random manner, so the fraction of training data and the test validation set will differ all the times. And 10 times I do my this kind of an experiment. So that will randomize my decision tree very well. And this we call, in colloquial term, we call it as a cross validation. So where we split, but we split it randomly 10 times. So different training data will be different from the training data set, different sets of data will be training data and validation data at different times. So this will make it more robust, and we call this as cross validation, and it's a very important feature for machine learning, producing machine learning model where you do not have the test data a priori.
Hello, sir.
Yes.
Sir, this is 80%, 20%. This is standard. And also, I have said 10 times. It is also standard, or
Yeah. So usually either people do, if there are very large amount of data, people do n by 10.
Okay, sir.
Or if there are a little small, less amount of data, let's say if you have 10 data, if you do n by 10, you have only one in the validation set, right?
Okay, sir.
So
Okay,
that's
sir.
why people sometimes try to do 80-20, but I mean 10%, 90% up to 60-40 is also okay. If you have enormous data, you can do it 60-40 too. But typically, this is by average people try to follow in cross validation kind of an approach.
Okay, sir.
Let's see. So,
Sir, in the graph, sir, why is the error less in the beginning, even in case of the test?
Even in case of a test, because you're generalizing in the beginning means what? Number of nodes is just one, let's say.
Yeah.
So one means it is generalizing very well. And in that case, what will happen? Let's say your test data. So this, I mean, this depends upon how you do your test data. So this curve could also be like this.
Yeah, it
This-
should be somewhat like that only.
Yeah, it could be like this. No, if your test data, if I give you test data which says mostly yes, then it could be like this. Na? The more you fit in, the bad it will get. Right? Or it could be like this in you are right. It could be like this in practical scenarios where we have an intermixing of yes and no answer. Then initially it will high and it will come down and then grow up. Whereas the test data will be like this. Right? That's what you mean. And this is our generalization error. Okay.
And same, why is the training data training error less in the beginning?
See, the analogy is the same. That is how the data distribution is. So this is, let's say, one of the examples could be like this. See, what does you need to know what does this mean? This means that you have only one node in the decision.
Yeah, less nodes. Yeah.
One node in the decision tree means what? That you are passing everything. I mean, if you have one node, so you have to categorize either something as positive and something as negative in one node decision tree. So if your training data, let's say, are all positive, then the training data will be less than two node decision tree. Error will little bit increase. After a certain point, it saturates and then it will come down. It all depends upon the data set that you have. You cannot fix a graph like this. In practical sense, this graph, the graph that you mentioned, could be mostly be in practical sense happen, but this is not a de facto that the graph will look like this. My only goal is that to show you it overfits after a certain point.
Okay.
So since you can by your common sense can get out the answers that what you will do, so the only remedy that I can see of is what we call as pruning. So we will try to see two things. One, the two algorithms. One is reduced order pruning, and one is rule post pruning. So as you can see that reduced order pruning means, let me give you a pictorial example. What does reduced order pruning does? So let us try to remember once again the classification example that we started off with. So we have some data as plus here, some data as minus here, and then let's say some data are minus here. There are some data which are plus, let's say one is minus here. Now see, traditionally what you are trying to do, you will try to do this, then 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 again this, then again this, then again this, because you want to eliminate this data. So this is overfitting. By this, what I mean, this is overfitting. If you have two attributes and classification is, so this is overfitting. Why we call it overfitting? Because maybe this particular data that we are trying to eliminate by fitting us, maybe it could be a noise. So now if you build a decision tree by overfitting such kind of a thing, since it's a noise, not an actual answer, maybe the test data do not want this region whole to be positive, but not this one to be negative. So you cannot generalize well. So what we can do, you can see that each of these lines that I have drawn is basically a particular value of the attribute that I tested upon, and my tree depth grows on. So what I will do there in that sense is, that either while growing, so this is while growing, I split one, I split twice, I split thrice. Either while growing, I stop splitting here, or maybe I split and make the depth. Later, I just remove some of the branching nodes from the lower depth and stay here. So this is what we call reduced order pruning. So each split will introduce a decision node in the tree. Each split that you make will introduce a decision node in the tree. Now you will just grow on like this. So sometime I will say that I will not grow beyond this point. This is my decision tree. That's what this approach will lead to. And if you think of growing beyond this point and then cutting over, so you may grow, and finally you can, for every training data, you can say which is plus, which is minus. Then you will say, okay, I just prune this part. I just eliminate this part. So which means that this pink color part will not be there. So this is the approach that I just mentioned is called reduced order pruning. And it is particularly useful when you have noise in the training data or you want to reduce the overfit. While you are cross-validating, you see overfit, you prune it or do not grow it up to a certain level. So these two factors are easily handled by this. The second approach, which we call as rule post pruning, this is basically after you build a decision tree, each path that you get is basically your endings of the values and all the paths are odd together. So therefore, you can make a formula that my attribute 1 can get value 1 and attribute 2 can get value something this, or I can say my attribute 1 get value 1 3, or I can say attribute 1 get value 1 2 and attribute 3 get value 3 1. So this is how the interpretation of decision tree in terms of Boolean formula. Now what we do is rule post pruning. We first formulate this formula from the decision tree. Here we have a, in case of reduced order pruning, you are only allowed to prune the lower part. That means the depth wise, the last formula at the endings you are trying to prune, because this ended with this, ended with this, ended with this, ended with this. Now you are allowed to prune these attributes only, not the previous attributes. However, see, we do not know what the unknown function we are trying to approximate. So maybe this attribute pruning or not using this attribute and then creating the tree would be more efficient. So here that ordering we relax. We can either prune this one or this one, either prune this one or this one, or even directly prune a branch. So this is called rule post pruning, where the preference bias, we can play around with the preference bias, that we can, after creating the tree, some preference we can eliminate some attributes which maybe you are thinking best. Depending on my cross validation, I saw that it is overfitting. I can eliminate and reorganize my tree or reorganize the rules. This actually is most modern technique. So everything you have seen ID3, including rule order, reduced order pruning, that is ID3++, let me say, everything is done by Quinlan in 1987. This approach is C4.5. The algorithm is called C4.5. Again, this is also done by Quinlan in 1993, I see. So this is what we could do if we could overfit the data. To end up, somebody had questioned in the last class that what happens if my attribute is continuous valued. For example, I have an attribute temperature and I would like to play or not. Let's say with the temperature, I have this data that if temperature is too cool, let's say 10, 12, 16, 22, 28, 30, 36, 40, 48. Now I will say, no, I will not play, no, I will not play, no, I will not play. Yes, I will play. Yes, I will play. Yes, I will play. Up to this, I will play. After 40, I will not play. This is, let's say, this one. There could be other attributes too. There could be other attribute values too dictating this final answer. Now, where do we split? Because temperature is a continuous quantity. What we will do, we'll try to see this pair here first. So, one of the splitting criteria would be temperature greater than or less than equal to 16 plus 22 by 2, which is basically 19. Here, temperature greater than or less than, we will split 36 plus 40 by 2, which is 28. Sorry, 38. Now, what I will try to see, I will again try to see my information gain with respect to only temperature and this outcome if I split here or if I split here. Whichever has the better information gain, I will select that particular temperature to be my attribute. So now there are two candidates you can see where to split between these versus this. Whichever gives me better information gain, I will split. So this is how we do with the continuous split, continuous continuous valued variables, deciding upon which of the attribute to select. We discretize the intervals in this way that where we will get a no yes answer, there those are my boundaries. There we can split, and we depend upon by selecting the information gain of those attributes. The other question that little bit came in the is that if we have some attribute missing, what we will do? Somebody had asked that if some attributes are missing. Some attributes are missing means that, say, suppose these are my attributes A1, A2, A3, and this is my answer in the classification. So let's say A1 gives V11, V21, V31. Yes. Suppose I do not know this. This one is missing. V21, V32. Yes. V21, V22, V32. No. So we have this way. So this is the case of if an attribute has a missing attribute value. So then what we do, either we see all the yes no's for these attributes and make this attribute whichever is the majority. So one approach is that we select majority value of this attribute and place it here. Let's say if we find V11 gives you more yes, then we will say, since this is a yes, we will say V11 here. The other thing is probabilistic approach. I will see that with V11, what is the probability of getting yes? With V12, what is the probability of getting yes? And so on. Now, for this attribute to be yes, you can see this could be V11, this could be V12, this could be V13, because this is missing. Anything can be possible. Now, what I will do in the branching, when I have V11 here for this, if I consider V11 into this attribute as this in this example, then I would also incorporate that probability value, let's say P1. When I get the data from here, I will multiply with this probability value and then sum it over to get the information gain. This is the probabilistic approach that we follow. So what will happen then if you get it V1, then you can see that how many attribute with V11 are yes. So here there will be some X number of pluses and Y number of minuses when V11, if you consider this as V11. If you consider this as V12, then again there will be some X dash number of pluses and Y dash number of minuses. However, when you are computing the information gain, there is a P1 probability of this to be V11, P2 probability of this to be V12. You just multiply those probability while adding up. So this is another approach that usually people follow for missing attributes. So as you can see, a decision tree learning algorithm can handle noise, can handle missing attributes, and also can handle this continuous valued variables in attribute set. So these are the advantages which we do not find in case of candidate elimination algorithms or concept learning algorithms. That's why decision tree is one of the most preferred one while learning this kind of Boolean concepts. I will end up here. You can also see some other attribute selection measures. So I have already uploaded a slide, and even in the chapter 3 of Tom Mitchell's book, you can find that if there are varying cost, you just have to normalize with respect to cost. So something what you do for attribute selection, if there are varying cost, since you select information gain for certain attribute, what you do, whatever be the value of the information gain, you make a square of that, and sometimes the cost of that attribute, you divide it to normalize. So some attribute may be more costly, some attribute could be less costly, and cost could be determined by the severity of the attributes and all. So therefore, you have to normalize and make a decision. So these are all small juggleries you can play around. There are many different such formulas. And remember that all these formulas has emerged because you are given certain application to solve, and you solve it better using this kind of normalization approach. However, the fundamental principle be, you have to select the attribute that apparently splits your space of classification boundaries very well. So with that note, let me end up the decision tree learning part. If you have any questions, you can ask.
Sir, can decision tree be used for regression problems?
See, regression problems means you want to predict a value. So if you could model your regression problem instead of a value prediction by a range kind of a prediction, then you can model it same as a classification problem. Are you getting it? Regression problems are basically predicting a value. So
yes, sir.
You can, let's say, what will be the rainfall tomorrow? This is a regression problem, depending on the past rainfall data of January month January. So now if this you could model this as a classification problem like this. Will the rainfall be 0? Will the rainfall be 0.1 millimeter? Will the rainfall be more than 0.2, between 0.3? Since you are bucketing it, that means you are making it into classes. Then you can apply the classification problem. There you will not get the exact value, but you will get a bucket. Let's say the rainfall could be 10 millimeter to 15 millimeter, yes or no. Get it?
Yes, sir.
Yeah. Any other question?
Are you uploading the slides on Moodle or?
No, in the web page. Immediately I do something, I upload the slides in the web page. Whatever I teach, that is there in a more formulated way in slides, but I prefer to teach this kind of a Blackboard because I think it connects you more. That's why.
Yes.
Sir, when some attribute is missing, you are saying we are calculating some probability, and then based on that we are processing subsequently. So how these probabilities are actually calculated?
Oh, these probabilities are calculated. See, the probability means that if I select this as V1, how many of them are yes and how many of them are no? That is the probability. See, here V11, one way I can select a majority. If I select V11, what is the probability of selecting here V11? So with V11 there, among the total, how many are yes and how many are no?
Okay.
Just think a little bit. Let this be a little bit of hint for you, and then think. Okay. What can you do with these probabilistic measures, with the missing attributes?
Okay. Thank you, sir.
Sir.
Okay. Yeah. Please.
Does the ID3 algorithm guarantee an entropy of 0 at the end of the decision tree?
No, three things can happen. As I always say, three things can happen. See, entropy of 0 can be guaranteed if after selection of certain attributes, you always get in one branch positive and other branch negative or something. I mean, if you can classify it properly. As in case of this example that we have drawn, let me show this example. See, if this was plus, then I can easily classify it using and finalize it, right? 1, 2, 3 lines will do, right? So then everything is crystal clear. Every boundary is crystal clear. But sometimes it may so happen due to this noise, you can see, we have to stop here. and we let's say the attribute set is also getting finished. So then we have to go by majority. If you have to stop here, instead of, though it is a minus, then we will categorize this class as a positive class, this whole class as a positive class.
Yes, sir.
So that means what, you are approximating a little bit, but it may help in generalization. So not always that your entropy becomes 0 or 1 at the bottom mostly. If that is the case, this is the best. That is the case, that means you have no training error, right? Got it? You have no training error, that means.
So in order to generalize, we can say that at the final step, we can have an entropy's limit that it will be up to 0.01
Yes,
or
you are
something
absolutely
like that.
correct. Effectively, what this reduced order pruning on post pruning does, it also tracks a value of the entropy and try to do it in a more formal sense, how much to reduce and all. Though it does cross validation and checks the accuracy, also it tries to have a limit on the entropy side as well, as you were saying, a threshold on the entropy side.
Sir, I have one question.
Sure.
So we are using this greedy approach for selecting the best attribute. So can there be any situation where this might give us a wrong answer? I mean, say our greedy selection says A1 is the first choice, but we might find that no, A3 could have been a better.
See, your question is again the feasibility of learning side. See, it is a possible scenario that it may happen, but you can if you see the proofs of decision tree learning generalization, probably it is approximately doing the correct thing. You are giving me a scenario where it may fail. It can, but if it sufficiently well behaved for training data, generalization boundary and theoretical results can show us that it sufficiently approximates the unknown functions to a greater extent, probably approximately less error.
Okay.
It may fail. It may fail. You are right that A2 taking A2 first may pass something. You never know because this is unknown. You are trying to I mean approximate an unknown thing by only considering that it has a pattern to approximate. That's it.
Okay, sir. Sir, are there any known situations like this where we have come across any situation? Or
yeah. Usually in medical diagnosis, decision tree has the most common feature of explainability, most explainable, because you know what decision you are making and that's why you are categorizing it as a positive or negative. That's why these are very much explainable. So that's why in medical domain sometimes we use this. But you see, medical domain is such a domain which has very less, small variations create big intricacies. So you cannot always say a person has tuberculosis by this decision tree only. There may be some other attributes which could be chosen first. So there it usually has a little bit of poor performance. But it is absolutely explainable as per its safety critical operations.
Okay, sir. Thank you.
Okay, so we are going more than the time that we have. So let me stop the recording.